in section 1.5, we want to talk about inverse functions. And so just some prerequisite information. Inverse, essentially what it does is it switches the domain and the range, or another way to say that is it switches the x and the y. And so letter A, two relations are inverse relations if and only if on one of the relations you have the element AB, and on the other relation you have the element BA. And so those x's and y's just get flipped. In letter B here, the graph of a relation and its inverse will be a reflection over the line y equals x, and we saw that briefly in a previous set of notes. And to find the inverse graphically, you're just going to pick some points off of the graph and then switch the x and the y and then replot those points. And so let's take a look at this just basic example. We want to graph the inverse of this function here. And so we're given these 4 points that make up the graph of f of x. And so I'm just going to plot these points really quick. -2, -1 would be this point right here to the left and down at -1. 0, 3 is going to be up here, and I'm going to go ahead and just connect those points to start making my function. 1, -3 is going to be down here, and I'm going to connect those points as best I can. And then 4, 2 is going to be right here, and I'm going to connect those 2 points just like that. Now, when I do the inverse function, the x's become the y's, and the y's become the x's. Or another way to say that is the domain becomes the range, and the range becomes the domain. And so, first of all, this is how we denote the inverse function, and notice that this does not equal to 1 over f of x. That's not what we're talking about when we talk about inverses. It's not a reciprocal, it's an inverse, meaning the x's and the y's switch. So for that first point, -2, -1, on the inverse, that's going to become -1, -2. I'm going to go ahead and plot that point. -1, -2 will be right there in red. 0, 3 is going to become 3, 0. And so 3, 0 is going to be right here. And I'm going to go ahead and connect those 2 points to start drawing my inverse function. The next point is going to be -3, 1 on the inverse, just switching the x and the y. So -3 and 1 is going to be right there. I'm going to go ahead and connect those lines as best I can. And then finally, 4, 2 is going to become 2, 4. And so 2, 4 is going to be here, and I'm going to connect those lines there. Now, it's a little tough to tell here. I've tried to use different colors, and I'm going to use a third color now to draw my line y is equal to x. And so if I do draw that line y equals to x, it's going to look something like this. And I'm hoping that you can possibly see that the blue, if I reflect it over the green line, is going to end up giving me the red graph. And so again, maybe a little difficult to see, but there it is. That's how you graph an inverse. Just pick some points on the graph and then switch the x and the y. Now, in this next part of the notes, I want to discuss with you when an inverse is going to exist. And just to put it simply, an inverse is going to exist if a function is 1 to 1. Now, we defined what 1 to 1 was back in section 1.3, and so just as a reminder, 1 to 1 means that a graph passes both the vertical line test and the horizontal line test. And so we're just going to make sure before we would look for an inverse that the graph would actually have an inverse by making sure that it's 1 to 1. So if you take a look at these 3 graphs, we'll take a look at this first one over here on the left. Does this relation pass the vertical line test? Can I draw any vertical line and have it only cross the graph one time? And the answer to that question would be yes, this is a function. So I'm going to say yes, a function. And the reason for that is that this particular graph passes the vertical line test. Now, the second question we want to answer is, does it pass the horizontal line test? Meaning, can I draw any horizontal line and only have it cross the graph once? And the answer to that question, as you can clearly see, is a definite no, because the one horizontal line I drew crosses the graph 3 times. And so no, the inverse is not a relation. And the reason for that is that this particular relation, the relation that we're looking at, fails the horizontal line test. Now, if I were to ask you a third question, is this function one-to-one, then the answer to that would be no, because it fails the horizontal line test, and in order to be one-to-one, you've got to pass both the vertical and the horizontal line test. Okay, if we look at the second graph here in the middle, does this graph pass the vertical line test? Yes, it does. So, therefore, this is a function. Secondly, does this relation pass the horizontal line test? And the answer to that is also yes. There is no horizontal line that you can draw that will touch the graph more than one time. And then what that means, what we can say based on that, is that this function in the middle is one-to-one, and therefore it has an inverse. Now, on this third graph, this graph is the worst one of them all because it does not even pass the vertical line test. So this is not a function because it fails the vertical line test. However, the inverse would be a function because it does pass the horizontal line test. So I'm going to say that yes, the inverse is a function because this graph passes the horizontal line test. You cannot say that graph number 3 is one-to-one, however, because it's not even a function. And in order to be a one-to-one function, you've got to first of all be a function yourself. And so because it does not pass the vertical line test, that third graph is not one-to-one.